So we've seen that if you want to find the CDF, or big F of x, from the PDF, which is little f of x, then you can just integrate it between the lower bound of the actual domain and then put x as the upper bound. And you'll see it either as f of t dt or f of x dx. If you've got f of x dx, it just means you'll be subbing in an x where there's an x already, which is fine. It works out okay. Now, there's a bit of a problem when you're dealing with a PDF that is a piecewise function, because there's a bit of a trick that you need to understand so that you get the right answer for the CDF. Now, if you divide it into sections, and here I've got an example, if we say that the PDF, or little f of x, equals something and something, I've just put g of x and h of x there to mean we've got some formula for it, and it's between, say, a and b, and then the upper section's between b and c, what you need to do is break it up and say, all right, for the lower section, or the section that's to the left, I'll do that first. I just need to use the normal procedure. Go from my lower bound up to x. In other words, make the upper bound movable so that we can say, what's the probability that that our random variable is this or less. So we want the upper one to be a variable. But then when we go find the upper section, we need to say what is the entire probability of the lower section. In other words, the area underneath the curve of this PDF for this whole lower section here. Now you can find that by just finding big F of B, which is that crossover point, and then adding it on to what you would have otherwise got by using this normal procedure. So we'll have a look at how this works in an example, and I think it will make more sense once we look at the picture. Now in this example, I've been given the PDF, and it's got a piecewise formula. It's 1/9 between 0 and 3, and 2/9 between 3 and 6. And so I've gone ahead and drawn the PDF just so I can get in my head exactly what it looks like. Now, don't forget that when we draw big F of x, or the CDF, we're literally just putting a dot in all of the spots to show the area under the curve up to that point. Now I'm going to show you two methods to do this. One just relies on graphing and using your graphing skills, and you might prefer that method. But I think also it's good to have a look at this method and why it also makes sense. Now here I've said that big F of x is going to have two parts to it. The top part is easier, and I can use my normal method. I'm going to integrate 1/9, and I'm going to go from my lower bound of 0 all the way up to a movable bound of x. So just following through what I've done here, if I integrate 1/9, I get 1/9 x, and then when I sub in x and then subtract the subbing in of 0, this part is going to be 1/9 x minus nothing. So that will be it. So if I write a good version here, or a finished version of f of x, big F of x, the top section is 1/9 x. But when you go to find the section that's further to the right on the graph and have a look at how its area under the curve is changing so that you can come up with a formula for it, it makes sense that you've got to look at what's happened up to that changeover point. Now, if we have a look here at the area under the curve at the crossover point where x equals 3, we've got an area of 3 multiplied by 1/9, so a total area of 1/3. And that makes sense with our new formula. When x is 3, the big F of 3 is going to be 1/3. So if I was graphing this, I could put a dot here and say, I know that the probabilities are going up smoothly, and by the time I'm at a value of x equals 3, the entire area under the curve showing me the chances of getting a score of 3 or less is equal to 1/3. So it goes up smoothly from 0 up to there, so I can reason that it's going to be a diagonal line like that. Now the second section also goes up smoothly, and I know that probabilities here have to all add up to 1, so by the time I get to my top bound, I can see that it must go up with another straight line like that, where the gradient of this one is going to be double that one, because they're going up twice as quickly, because the area is a rectangle that is twice as tall. Now we can come up with reasoning to say, hey, these probabilities here are going up nice and smoothly, but we've got to acknowledge that if we're finding the probability that x is, say, 4 or less, or 5 or less, or something like that, we have to acknowledge that from here down, we've got a known quantity. We know that the chances of x being 3 or less is 1/3. So we have to start with that 1/3 and say, well, we know that, but then how's it going upwards from there? Does that sort of make sense? And that's why we need to say, well, what is the big F of 3? In other words, what is the accumulated area under the curve up to that point? Because if we're looking at the formula for how this part changes, we need to take that into account and add that on. So we start with that. Then we say, let's look at the formula for this part. So our lower bound will be the 3. Our upper bound is movable because we want to be able to change it. And we integrate 2/9 with respect to x. So that section says to us, okay, we've got our third, and we can either get it by looking at this area here and reasoning that it is a third, or we can just plug in the x value of 3 to the formula that we've already got for the lower section. We've started with that, and now here we've got the integral of 2/9, so we've got 2/9 x. Now we need to sub in our upper bound of x, which is movable, so that'll just give us 2/9 x. But then we need to subtract the subbing in of the 3, and that'll give us 6/9 or 2/3. And we have to add all of that to, sorry, I forgot to write it in the beginning, that third that we started with. Now you'll notice that we've got 1/3, and then we're subtracting 2/3. So what that's going to give us is a finished answer of 2/9 x minus 1/3. Now let's look at another simpler method of just working out what the equation of each of these lines would be. They're straight lines, so if you're able to draw the CDF based on the PDF, then all you really need to do to come up with these is to say, well, what's the equation of this line? If we put it in gradient intercept form, we know that it has a gradient of 1/9, so it will just be 1/9 x because it clearly goes through the origin. This bit is a little bit trickier, but there's two methods that we could use here. We could throw it into this formula and reason that if we know the gradient, which is 2/9, and we know even just one point on the curve, well, we know 2. We know that when x is 6, y is 1. That would be a nice simple one to put in. Or we know that when x is 3, y is 1/3. Let's put this 6 and 1 in because that's the easiest one that we can see to work with. Y minus 1 and x minus 6. Now if we expand our brackets out, then we've got y is equal to 2/9 x, and we've got 1, which is 9/9, minus 12/9, so we've got minus 3/9 or minus 1/3, which is the exact same answer that we got over here, probably with a lot more effort. This one had more effort, I mean. This one was probably easier. You could also do a bit of problem solving and say, where would this line cross the y-axis if it kept on heading down? Now, between this section here, it drops 2/3, doesn't it? And here it goes across 3. So if it's going to go across 3 again, it's going to drop another 2/3, isn't it? And it's already at this point sitting at 1/3, so it's going to drop another third. And I can just use reasoning there to keep things in the same ratio and come up with the y-intercept. So now I can say, I know the gradient of this line, it's 2/9 x, and the y-intercept is minus 1/3. And that would probably be the easiest way yet of coming up with this formula.